Hi, I'm Jade, and today I'm going to show how to turn println into wintln. You can find a link to these slides on the bottom left. This idea was inspired by my friend the 6B4C on Twitter, and I've further developed it into a crate called wintln that is available on the crates registry. This talk demonstrates the prototyping process that went into that crate. This is Carly and Safer Station. You'll be seeing some more of them in the slides. They're a friend. So I remember reading about a binary exploitation technique where you could overwrite some function pointers in memory and get the program to go elsewhere when functions from external libraries such as the systemc library, libc, are called. Let's try writing a program and see what we can find of those. So we're going to make a string hello bang bang con, and then we're going to write it to the screen. So we're going to use the write call, and we're going to pass a file descriptor number 1, which is standard output. And then we're going to give it a pointer to our string. We need to turn that into a void pointer, so let's cast that. And then let's give it our string's length. Then we get an error that we need to use an unsafe block, so let's do that because raw pointers are unsafe to use. And now let's compile and run our program. Let's look at it in a debugger and see if we can find those function pointers we're looking for. So we're going to set a breakpoint at the start of our program. And then we're going to disassemble our program. So we see at the bottom here a jump keyword pointer RIP plus some offset. The square bracket syntax there is a pointer dereference. So it's dereferencing the pointer 39599 bytes after the current instruction. So if we look at what's actually there at address 555 whatever, then we see that there's another pointer. And we find that if we look at what's at that pointer, we find it's a pointer into write in the systemc library. So that's what we expect to see. However, how would we find this address? So in order to answer that, we need to look at what an elf is. So an elf is the executable format used by Linux and BSD. It loads various sections out of your executable into requested locations in memory with requested permissions. And it also allows for dynamic linking, which means that you can have libraries that you can replace without having to recompile your program. How do they do dynamic linking? So on Linux, dynamic linking is accomplished by the dynamic loader, which gets at your program before you get control. And it will load all of your dynamic libraries and set relocations of all of the functions that you call in those dynamic libraries to pointers to the actual functions in memory. So we want to read a relocation, and for that, we're going to use readelf. So let's try that out. So we're going to read the help page for readelf and see if we can find something to do with relocations. And indeed, we have -r, which deals with relocations. Okay, so let's try looking at that. So we're going to go look at the relocations of our executable and search for the write function in glibc. We find that it is indeed there and it is at some offset. We don't necessarily know what this offset is for yet, but let's guess that it's probably from the start of our program. We can find the start of our program by running info-proc mappings in GDB. What this will do is it will find all the regions of memory that our program owns. And we see that the top one is at offset 0 of our executable. So that probably confirms our hypothesis already, but let's continue testing it. So we're going to add the offset that we got from readelf to the number we got from GDB for the base of our program. And then we're going to dereference that as a pointer. And we see a 7FFF value that we saw before. So that already looks promising. And indeed, if we look at an instruction there, we see that it is part of the write call. So that's good. Let's start writing a wrapper. So this wrapper has the same signature as the write function in libc, except it's translated into Rust syntax. First, to wrap this, we need to turn our input into a slice of bytes. And then we take that slice of bytes and then we turn it into a string. So it's a reference to the string that we were given. Then we convert that string to UTF-8. Well, strings are UTF-8. And then we need to copy that into heap memory as an own string and then uwuify it. So now we have an uwuified string. So now we need to write it to the screen. However, since we are going to overwrite the pointer to the write function, we have to store away its original value because we can't call it through its normal method. So we're going to make a global variable that we're just going to store the address of the write function at. So in our wrapper, then we are going to use that global variable to call the write function, the original one, with our uwuified string, with the same file descriptor, and with the uwuified string's length. We then have to lie to our caller that we have written exactly how much they've asked for, because otherwise it will go badly if we say actually wrote more than they asked for because we added some characters while uwuifying. We then have to also add our uwuification library. Next, we need to overwrite that function pointer. So we're going to take in the hex address from the command line that we had gotten from readelf, and then we're going to add that to the base address of our program that we got from before. Next, we're going to dereference that pointer and overwrite it. But first, we have to store it away in our global variable. So we're going to use Mem Transmute, which what that does is it converts a value of any type in Rust into any other type. It is extremely unsafe and therefore a lot of fun. So we turn the dereferenced value of the relocation, that is to say the address of the actual write function, into a function pointer and then store it in our global variable. Then we overwrite the relocation with our replaced version. Then we rebuild the program. We redelf it again because it's possible that the relocation moved because we added a bunch of code. Then we get the address and we set it as a command line argument with set args. And then we run our program. Unfortunately, it does a segmentation fault. Let's see if it is at least doing what we expect it to do. So the address that we have is 555 something, which is what we saw before. And if we look at what's at that address, we indeed see a function pointer. And if we look at what's at that function pointer, indeed it is a function pointer to write. So it is what we expect it to be. But the reason it failed is because, as I said before, the ELF format allows you to specify permissions for regions of memory. And so the relocations region is actually read-only, and therefore our write to it failed. So all we have to do is we have to tell it that actually we do want that to be writable. And for that, we use mprotect. So what we're giving it is the address of the bottom of the 4096 byte page or region of memory that the function pointer that we're trying to overwrite is at. And then we ask it to change an entire page at once. The reason for this is that the granularity of memory permissions is one page. We do some bit tricks to get the bottom of the page. Then we go to readelf again and go and get the right offset for our modified program. And we set the arguments and we get hello uwu con uwu. Yay! All right. So this also works on println because println internally calls write. How do we do this properly though? It turns out you're not actually supposed to redirect control flow of programs, and generally that's considered a security vulnerability. So there's various mitigations that are used to stop people doing this. One example is layout randomization. The program is not normally loaded at OX555. It is loaded at a random address that changes every time, which means that shenanigans like this aren't supposed to work. It only works because it's in a debugger. The other thing is that the relocation section that we're trying to overwrite is write protected, which is called relro, relocations read only. We also want to find the symbol ourselves, and that's how we would get to what the println crate does. How do we start at finding the symbol? Well, we want to look at readelf output, and we find that we have this relocation section relay.dyn, so we need to find where that is. And so with this convoluted page of diagram that was made from reading man5 elf for a long time, we can find the symbol by looking at our program information. So the starting point that you would use is getOxval, which looks at information that the kernel returned while loading the program, and that will tell us where our program headers are. And then from that, that's just the executable that's mapped directly into memory. So then you essentially read the ELF file as if it was on disk but just like out of your own memory. You look at the program headers and use those to find your program base address and also where the dynamic table is. From the dynamic table, you know where the relay table is, where the symbol table is, and where the string table is. From the relay table, you go through each entry, and then you can find the symbol table offset of each entry, use that to index into the symbol table, and then that will tell you the string table offset of the name of the function. You go through all of the relays until you find right, and then you know what your offset is, and then you can implement wintln. So this is very close to what wintln is that we've already built in 10 minutes. So that's all I have. Enjoy the rest of your Bang Bang Con.